Okay, I'd like to get started, if we could. If you haven't turned in your observing project, please do so. So let's get started. Welcome to lecture 13 of the planets. Believe it or not, the semester is about half over. Can that really be true? Seems impossible. We're going to talk today and Thursday about the atmospheres of the terrestrial planets, with a special emphasis, of course, on our home rocky planet. So this is a topic that will be maybe the most important of the whole semester, especially Thursday's lecture. So if there was ever a lecture to come prepared and with your brain turned on, it will be Thursday's lecture. Today's lecture will be a preparation for Thursday's lecture. And I'll remind you that, as always, there's homework due. It's to read chapter 10. So this is such an important chapter that I want to emphasize. Reading chapter 10 will give you knowledge, frankly, you'll use for the rest of your life. You'll learn about the health and structure of our Earth's atmosphere, and you'll learn about the origin of global warming, the greenhouse effect, global climate change, and ultimately you'll learn what we can do about it. So this chapter has something to do with your own health, the health of your children, your children's children, and so on. So by all means, read chapter 10. The homework assignment is, as usual, in Mastering Astronomy. And, of course, it's due Friday at 6 p.m., as always. At the end of the lecture, if you have not already turned in your observing project, please do so. It only has to be a sketch of the moon during the eclipse. It takes 30 seconds. That's good enough for us. And I want to just touch on the last week's lecture. Last week we talked about the rocky planets, but not the atmosphere, but instead the interiors, the interior structure of rocky planets, how we use earthquakes and seismology to sense via the sound waves the structure of our Earth and also the crust, and how the convection of heat through the mantle causes a rise of warm rock that rubs against the crust, moving the crust around, breaking it into fragments that causes plate tectonics and ultimately causes earthquakes. And I just wanted to remind you, as you all know, the subject of plate tectonics and earthquakes is, of course, one very important to us here at Berkeley, because the Hayward Fault runs smack through Memorial Stadium. As you see here, here's the Hayward Fault. It runs right through the football stadium. There are some fractures like so. And so over the upcoming decade or two, the football stadium is literally going to slice in half. Probably if you come back in 15 or 20 years, it will have moved several inches, one half relative to the other. And there may, in fact, be a large earthquake someday. The Hayward Fault that we live on is due. The last earthquake, major earthquake on the Hayward Fault that campus sits on was in 1868, and they tend to happen about every 150 years. You can do the math. So we are due for another large earthquake right here on the Hayward Fault. Probably in the next 10 to 20 years, there's about a 50% chance of a pretty big one. You can see that formally the probability is a 63% probability, misspelled with the T out, 63% probability of a magnitude 6.5 earthquake or more in the next 25 years. So, every year that goes by, there's another few percent probability that we're going to have the 6.5 earthquake. And someday, maybe with the Hayward Fault plus the San Andreas Fault, there's a chance of an 8.0 on the Richter scale. So earthquakes are a reality, and as all of you know, the buildings on campus have been retrofitted to be seismically as safe as possible, but there are no guarantees. The freeways, the bridges, the buildings are all susceptible to a large earthquake. In today's lecture, we're going to talk about the atmospheres of the rocky planets. And we ought to start right here at the Earth. It's remarkable when you look at a picture of the Earth's atmosphere, how thin it is, how delicate it appears, how fragile it appears. You owe your existence, of course, to the Earth's atmosphere. Every moment that you breathe in and breathe out, you are taking advantage of the oxygen in the Earth's atmosphere, and you are, of course, exhaling carbon dioxide. And so you are a living part of the atmosphere. You need it. And as you'll see in today's lecture, there's a feedback mechanism between the exhaling of CO2 and the inhaling of oxygen. So it's a very fragile, thin layer of gas to which we owe our existence here on the planet Earth. Here's another picture taken from the space shuttle. You again see how thin and fragile the Earth's atmosphere is. By the way, it's remarkable that such a thin layer of gas can persist reliably year after year, decade after decade, century after century, millennium after millennium, so that we humans could evolve for the last 2 million years as we have. If at any moment the atmosphere went away due to a volcanic eruption, an impact from a comet or an asteroid blowing the atmosphere away, any sort of catastrophe would have ruined the atmosphere and hence ruined our lives. So there's something remarkably important about the stability of our fragile Earth's atmosphere. And indeed, the Earth's atmosphere is a dynamic, active place. Of course, there are clouds, there's convection of heat from the surface, there is a protective layer that we will talk about, the stratosphere, that protects us from ultraviolet light coming from the sun. The stratosphere, with its ozone, as we'll discuss, is very important to life. There are cycles in the Earth's atmosphere. Water, carbon dioxide, other molecules go up into the atmosphere, and then they come down to the surface. In the case of water, it's rain. In the case of carbon dioxide, it's the animals and plants that absorb the carbon dioxide, die, get subducted down into the mantle, and come out again in the form of volcanoes. So there are cycles that regulate the amount of different molecules in the Earth's atmosphere. And of course, the Earth's atmosphere protects us from the debris of the solar system. The asteroids and comets that otherwise would fly through the solar system, collide with the Earth, and impact the Earth, certainly destroying the oceans and the atmosphere, are softened and usually vaporized by the Earth's atmosphere. So the Earth's atmosphere offers a protection against the impacts from asteroids and comets and meteors that otherwise would kill us. Now, of course, the Earth's atmosphere contains several dominant molecules. You learned about this in third grade or second grade. Nitrogen is the dominant molecule in the Earth's atmosphere, then oxygen that we breathe, then carbon dioxide is the third most common. We use all of these molecules in different ways. Oxygen, of course, is necessary for respiration of animals. The oxygen also combines into ozone to protect us from UV light and from the meteorites, as I mentioned. You'll learn in Thursday's lecture that the carbon dioxide in the water vapor traps infrared light. And that greenhouse effect allows the Earth to be as warm as it is. Otherwise, it would be frozen. Let me say that again. The Earth's surface would be a frozen wasteland if it wasn't for the greenhouse effect caused by water vapor, carbon dioxide, and other greenhouse gases. That will be the topic of Thursday's lecture. So the Earth's atmosphere plays many roles in our lives. And I want to start by probably reminding you, of the structure of the Earth's atmosphere. It's not uniform, as you can see. Just by taking a picture of the Earth's atmosphere, you see layers. And I'd like to, in a few slides, tell you about the different layers in the Earth's atmosphere and what each layer actually means. So to start, here is a schematic of the Earth's atmosphere. The lowest layer that you will spend almost your entire life in is called the troposphere. Easy way to remember this, the bottom 10 kilometers. Here it says 14 kilometers. The bottom 10 or so kilometers, i.e. 6 or 7 miles, is the troposphere. Even if you climb to the top of Mount Everest, you're still in the troposphere. Airplanes flying at 35,000 feet, do the math, that's about 6 miles, you're still in the troposphere. So the lower layer of the Earth's atmosphere that you breathe in and out every moment of your life is the troposphere. Above that layer is the stratosphere, going up to some 50 kilometers. It's a very important layer, and I'll describe in a few minutes how the stratosphere contains ozone that traps the ultraviolet light, which otherwise would cause hideous mutations. And then on top of the stratosphere is the mesosphere, and there's an exosphere and an ionosphere. I'll mention them briefly in a few minutes. Before I do, let me remind you of, whoops, lost my microphone again. Let me remind you of the molecules that are in the Earth's atmosphere. Nitrogen, number 1. When you hear the term nitrogen, don't let your eyes glaze over. It's not atomic nitrogen. Yeah, it's true that nitrogen sits here on the periodic table. It's an atom with 7 protons and 7 neutrons for a total of 14. But the nitrogen that's in our Earth's atmosphere is not atomic, but molecular. It's a molecule of nitrogen, 2 atoms, as you see here. So the nitrogen that we normally talk about in our atmosphere is a diatomic molecule, as is oxygen. Same thing, don't let your eyes glaze over. There are atoms called oxygen, but it's 2 of them bonded together that make molecular oxygen that you breathe. And of course, we owe all of the oxygen in the Earth's atmosphere to photosynthesis. And then there are other molecules that contribute less to the inventory of molecules. Argon is the next most common gas. There's, of course, carbon dioxide that will be almost the entire subject of Thursday's lecture, a greenhouse gas. And then there are other molecules floating around the Earth's atmosphere. Water vapor, carbon monoxide, neon, methane, krypton, and other trace amounts. By the way, I can't help but mention, you'll hear terms like methane and ammonia. And at first you might think to yourself, well, what is methane exactly? It's a word, but what's in it? You should always translate the word methane or ammonia into what the structure of the molecule is. That helps you understand it. So, for example, methane is a carbon atom with 4 hydrogens. Ammonia is a nitrogen atom with 3 hydrogens. So when you hear methane or ammonia or any molecular name, it's good to refer back to what that name is shorthand for. So this is what's in the Earth's atmosphere. Here it is again in a pie chart. You've got your nitrogen dominant, oxygen next, and then a sliver of other gases. Argon that I mentioned, carbon dioxide is the remaining most common molecule, and then you see some others there that are exist in the Earth's atmosphere in trace amounts. One of the things that you know about the Earth's atmosphere, and this is not obvious, is that the Earth's atmosphere is nearly transparent. You can see right through it. How do you know? Well, when you look up at night, you see stars. If the Earth's atmosphere had any opacity, you would barely see the stars, if at all. Moreover, sunlight streams down from the sun through the Earth's atmosphere and hits the surface of the Earth, with hardly any of the sunlight being absorbed or scattered on its way through the Earth's atmosphere. This is lucky because, of course, we make use of sunlight, both animals do and plants, for energy needs. But having said that the Earth's atmosphere is transparent, it must not be perfectly transparent. If the Earth's atmosphere were utterly transparent, you would look up into the daytime sky and it would be pitch black. You wouldn't see anything. It would just be dark. You'd be looking out into the cosmos, the darkness. Even if the sun is up, if the Earth's atmosphere were utterly transparent, well, then you would just look right through it into the darkness of the universe. But you don't see that. You see a blue sky. Why is it that the sky is blue? Well, clearly the answer is a tiny fraction of the sunlight worming its way down from the sun, trying to penetrate the Earth's atmosphere. A tiny fraction gets scattered. Light that would have hit over there, sunlight that would have hit over in some direction or another, gets scattered off of the molecules, nitrogen and oxygen, and scattered into your eyeball. So the fact that the sky is blue tells you that a little bit of the sunlight is not making it directly down through the atmosphere. The Earth's atmosphere is not perfectly transparent, but some of that light gets scattered. And clearly, it's preferentially the blue photons, the bluest wavelengths of light, that get scattered more than the green, the yellow, the orange, and the red. Blue photons, for whatever reason, and I'll tell you in a moment, scatter off of the molecules in the Earth's atmosphere more efficiently, so that when you look in any direction during daytime, you see blue light. Where did the blue light come from again? Sun emits the light, hits some poor unsuspecting molecule in the Earth's atmosphere, scatters off that poor molecule into your eyeball. And so the sky looks blue. Clearly what's happening, as you see in this diagram, is that as an observer, the sunlight over here is hitting molecules. Some of them are getting scattered in all sorts of directions, the blue photons preferentially, and every once in a while, one of those blue photons happens to be scattered into your eyeball, and you get to see that scattered blue photon. It turns out that there is a process of scattering in which small particles, the size of molecules, preferentially scatter blue light over the green, yellow, orange, and red. And that process is called Rayleigh scattering. It's a complicated process that I won't tell you how and why it works, but electromagnetic waves, i.e. light, preferentially scatters off of a molecule in a way so that it's the blue photons that get scattered more efficiently than the longer wavelength photons. And in fact, the relationship, which you don't have to remember, but it's kind of cute, the intensity of scattered light is proportional to 1 over the wavelength to the 4th power. That's a very high power. So a wavelength that's twice as long, 2 to the 4th power, 2 times 2 is 4, times 2 is 8, times 2 is 16. So blue light at 400 nanometers of wavelength compared to very red light at 800 nanometers, twice the wavelength, those blue photons get scattered 16 times more efficiently using that wavelength to the 4th power rule. So you can see that due to Rayleigh scattering, as it's called, blue light gets scattered way more efficiently than the longer wavelength light, like the yellow and the red. And that's why the sky is blue. And here's a graph showing that. Here's wavelength in nanometers. 400 nanometers is over here. The blue light scatters very efficiently. And then over here is red light. The red light gets scattered, sure, but much less efficiently. So when you look up into the daytime sky, it's mostly the blue light that got scattered into your eyeball with only a tiny amount of the green, yellow, and red. By the way, I have a few quiz questions. So if you have your multicolor pieces of paper, do we have any extras? Uh-oh. Well, we don't. So if you don't have your multicolored pieces of paper, you'll be out of luck. That's the way it goes. So here's a question, the first of a few quiz questions. What about at sunset? Have you ever sat on the beach, watched the sunset over the Pacific Ocean? The sky doesn't look blue toward the twilight. It looks orangey red to me. Here's what I mean. If you look over the bay toward the Golden Gate Bridge, you see a red sunset. Why is it, if Rayleigh scattering scatters the blue light preferentially, why at sunset does the sky look red, or reddish, or orange? Well, the answer is that when the sun is on the horizon, as you see here, the poor photons from the sun have to travel through a huge distance of the Earth's atmosphere. And that very long path length through which the photons have to travel when the sun is just setting on the horizon, or even below the horizon, those poor photons have to skim through the Earth's atmosphere, traveling 1,000 miles through the Earth's atmosphere, not taking the shortcut right from above. And in that case, the blue photons get scattered so efficiently that they're all scattered away. And there are no blue photons left at all. They've all gotten scattered away. Some of them got scattered down to this person here, and so on. And all that's left at sunset or just after sunset, all that's left, with the blue light having been scattered and even most of the green light, all that's left is the red light. So the reason the sky has that gorgeous orangey red color at sunset is indeed, again, Rayleigh scattering, the blue photons having been scattered away, leaving only the longer wavelength orange and red photons, giving you this beautiful sunset color that we all love so much. Here's a little quiz question. It's kind of a strange one, actually. Suppose in a certain city there are streetlights that are white, and the streetlights shine not just on the ground, but like they do, shine up into the night sky. The question is, will the night sky, due to these streetlights, appear faintly blue, faintly red, faintly white, or white but missing the blue and the red? You want to show me your answers to this question? Take a shot at it? This is a pretty tricky question, I think. Blue, red, white with no color, or white missing the blue and the red? Well, I can tell you, looking out into the audience, there's lots of colors. Looks like the full rainbow. Actually, I see more letter A answers than any other. And actually, that's right. The reason A is right is that it's Rayleigh scattering again. You know, if there are white city lights and the white light from the city shines up into the Earth's atmosphere, most of those photons travel out into the universe, lost from the Earth. Why? Because the Earth's atmosphere is mostly transparent. But those photons that get scattered preferentially are the blue ones, and they get scattered maybe back into your eyeball. They go up into the night sky, scatter off molecules, come back, mostly the blue ones scattering more efficiently. So even though your eye isn't sensitive to colors at night, the cones among the rods and cones in your retina, the cones aren't active when the light level is low. So if you've noticed, you don't have very good color vision at night. Nonetheless, with a good camera, you would be able to tell that the night sky is actually faintly blue because of the Rayleigh scattering that preferentially scatters the blue light. Now, there's another aspect of the Earth's atmosphere that is important that we'll talk about mostly next time, and that is the trace constituent carbon dioxide. And the remarkable thing about carbon dioxide is that even though less than 0.1% of the Earth's atmosphere is composed of carbon dioxide, amazingly, over the course of time, you're seeing about 60 years on the horizontal axis. Over the course of time, over the decades, since your parents were born in the 50s or 60s, the amount of carbon dioxide in the Earth's atmosphere has been rising steadily and dramatically. And so it is that rise in carbon dioxide that we'll talk about next time. It's due to the fact that here in the modern era, we humans are burning what are called fossil fuels, fuels that come from the fossils, coal, natural gas, and liquid gasoline. And when you burn those fossil fuels, coal, gasoline, and gas, the daughter product, the byproduct, is carbon dioxide. So we are generating enormous amounts of carbon dioxide. We humans are spewing it out into the Earth's atmosphere. And we'll talk next time about what the consequences of that carbon dioxide is. Now, I want to talk a little bit about the structure of the Earth's atmosphere and where they come from. Take-home message. Where does the Earth's atmosphere come from? Where do all of these gaseous molecules come from? One simple answer: volcanoes. Volcanoes on the Earth spewed up gases over the millions and billions of years, and the same happened on Venus and Mars. In all three cases, their atmospheres are a result of gases spewed out by volcanoes, water vapor, carbon dioxide, nitrogen, hydrogen sulfide, ammonia. By the way, there's ammonia, NH3. On the Earth, various chemical processes got rid of some of the molecules. The remaining dominant molecule, of course, is nitrogen. Carbon dioxide mostly got dissolved in the oceans, absorbed into plants. Notice that oxygen let me repeat, oxygen does not come out of volcanoes. You don't see oxygen here. Why is that? Why doesn't oxygen just come out of volcanoes? Well, the answer primarily is oxygen is very reactive. You've heard of the term oxidizing or an oxide. Oxygen as a molecule and as an atom reacts very efficiently with other molecules. So if there had been any oxygen to be spewed out from the volcanoes, it would have reacted early on, actually before it even came out of the volcano, and when it did come out of the volcano, react immediately with other molecules and would be gone. In particular, iron rusts, and you've heard of iron oxide. We talked about it as the constituent of the surface of Mars. Oxygen is so reactive that it reacts with rock to produce rust. So oxygen is not something that comes out of the volcanoes. And of course, as we'll discuss in a minute, the oxygen on Earth came from life. Before there was life on Earth, in particular plants doing photosynthesis, there couldn't have been any oxygen. On Mars and Venus, why is there no oxygen in their atmospheres? Well, there's no life. There's no plant life to produce the oxygen. So Mars and Venus are left just with carbon dioxide as the dominant gas. By the way, Mars is a particular case. You remember from the lecture on Mars, it's a small planet. We don't normally think of it that way. It has 1/10 the mass of the Earth. And because Mars has such a small mass, it's gravitationally unable to hold on to much of an atmosphere. The molecules moving around simply escape. By impact, by heating, the molecules escape the weak gravitational field of Mars. So one of the primary reasons Mars doesn't have a substantial atmosphere is that it's, as a planet, gravitationally too feeble to hang on to its molecular constituents. The molecules literally achieve escape velocity, like a rocket, just by their normal molecular motions. But it's the volcanic outgassing that dominates. And so one take-home message for this whole course is that the atmosphere of the Earth and of other rocky planets is in fact due to the volcanic spewing out of various molecules. And so you can sort of see that there's a cycle that must be happening because volcanoes keep happening. Every year there's another volcano that goes off somewhere on the planet Earth, usually several volcanoes. So when a volcano goes off and molecules are spewed out, why doesn't the Earth's atmosphere just keep getting enriched thicker and thicker and thicker? Well, the answer is there are cycles. The gases escape, but they get absorbed by plants. They react with the dirt. They get absorbed into the oceans and eventually subducted down into the mantle. So the gases that come out in a volcano eventually end up back in the planet Earth. But now, what about oxygen? Clearly the most precious of the molecules in our Earth's atmosphere. Where did oxygen come from? When did the Earth become, how shall we say, blessed with oxygen? Well, the fossil record is very clear about this. We know, and you learned this in 3rd grade, that we owe oxygen today to plants and the photosynthesis, including even the algae that covers the lakes and the oceans. There are bacteria, there are plants that themselves engage in photosynthesis, and they, of course, absorb the carbon dioxide and produce oxygen. So these little itty-bitty so-called blue-green algae or cyanobacteria do a lot of the work, actually, in converting carbon dioxide into oxygen. And the most amazing fossil record of the origin of oxygen on the Earth comes from these very strange mounds that you see here. They are rocks at the bottom of the bay in Australia. And you can go there if you've ever been to Perth. It's a few hundred miles north of Perth, Australia. You can go to Shark's Bay and see these striated rocks that are the fossilized forms, the rock descendants of the blue-green algae that thrived on the planet Earth over 3 billion, with a B, years ago. When you cut these rocks open, you see the layers of algae in this blue-green algae year after year after year, like tree rings that built up, showing that there was essentially plant life, algae that was engaged in photosynthesis that produced the first oxygen on the Earth. Imagine the first 1.6 billion years of the Earth's existence. There was no oxygen at all. If you could go back in time and show up on the Earth 4 billion years ago, there would be no oxygen. It was about 3 million years ago that these primitive single-celled algae engaged in photosynthesis produced oxygen, and we see the halting, stochastic, sort of periodic attempts to enrich the Earth's atmosphere with oxygen in these rocks called banded iron. This is just iron, rocks that would be just made of iron. But as the oxygen built up in the Earth's atmosphere and then got absorbed and then built up again and got absorbed, you see different layers of iron rusted. The red color is a clear sign of the rust that occurred in some years but not other years as oxygen began to build up. And when you radioactively date these rocks, they are about 3 billion years old. So 3 billion years ago, oxygen was turning on and off, barely getting going in the Earth's atmosphere, getting a toehold. By the way, you can buy banded iron if you go to a rock store. You can buy it, for $20 or $30. You can buy little bits, pieces of a few inches across of this banded iron. I've bought some myself. I love doing this because when you buy a banded iron rock, you're buying a rock that is not only 3 billion years old, but it serves as a visible testimony to those early days of oxygen enrichment in the Earth's atmosphere. Kind of a dramatic moment, because without oxygen, the animal kingdom could not have taken place. So this banded iron is an extraordinary visible record of those early days 3 billion years ago when the early photosynthetic plants produced enough oxygen to enrich the Earth's atmosphere with it. Now, of course, you can build up gases in an atmosphere, but some of it goes away. And I just want to mention briefly, it's not very important, that there are ways to gain gases. I've already mentioned volcanism. You can evaporate water. That enriches the atmosphere. You can have impacts hit the ground and spew up vapors. But you can also get rid of gases in the Earth's atmosphere. And here are just a few cartoons that show you how to get rid of gases. Gas can condense, and then it's lost from the atmosphere. Gases can have molecules that move so fast that they achieve escape velocity and leave the Earth or leave the planet. You can have molecules in the atmosphere that engage in chemical reactions and therefore are lost from the Earth's atmosphere. You can have impacts hit the ground and blast away the Earth's atmosphere. So there are ways to lose the molecules in the Earth's atmosphere, and there's ways to gain them. A quick inventory of the atmospheres of the 4 rocky planets and the Moon. I have not mentioned Mercury, the planet Mercury, closest to the Sun. Why? No atmosphere at all. And so it's easy to keep track of Mercury's atmosphere. It's just a barren rock. Venus, thick carbon dioxide atmosphere, so thick that it's opaque, as you can see with clouds, mostly carbon dioxide. The Earth we've already talked about, nitrogen, oxygen, argon, carbon dioxide. The Moon, no atmosphere at all, as you all know. And then finally, Mars, again, we've already talked about it, has a thin atmosphere, 1% of the Earth's, and it's entirely carbon dioxide. So that's just a quick tour through the Earth's, through the various atmospheres of the different rocky planets. Now, one thing that is a little, or should be puzzling to you, gas has temperature and pressure, like a balloon, like the air in a balloon. Why doesn't the gas in the Earth's atmosphere expand and leave? Why doesn't the atmosphere just escape the Earth or escape other planets? And the answer in a nutshell is that the gas in any atmosphere, yes, it has temperature and pressure. We'll talk about it in a minute. But they're held, the molecules are held to the planet by gravity. And so even though the molecules are moving around quickly, some of them moving upward and might escape, it's gravity that holds them to the planet. Now, I mentioned briefly that the molecules are moving around and they have temperature and pressure. But I didn't tell you what temperature is. You think you know what temperature is because you've been using that word ever since you were a kid, and you think you know what pressure is. Let me tell you a little more precisely what temperature and pressure actually are. Temperature is a word we use that actually represents the typical speed with which the molecules are moving around, the average speed, the typical speed. So on the left is shown a schematic of molecules moving around at some temperature, 150 degrees Kelvin. I guess that's about minus 120 Celsius, so that's cold. Nonetheless, even at cold temperatures, molecules are moving in random directions with a range of speeds. The molecules in this room, the nitrogen and the oxygen molecules in this room that you're breathing in, each individual molecule is moving in a certain direction on its own with a certain speed in some range with some distribution. And the typical speed, the average speed of the molecules in a batch of molecules is characterized by temperature. The higher the temperature, the faster the molecules are moving. So here's some cold gas where the molecules, as shown by the arrows, are moving relatively slowly. And on the right is a hot gas, 300 Kelvin. That would be about 27 degrees Celsius. Hotter gas, the molecules on average are moving faster. And so temperature is just a shorthand word that we all use that really represents how fast the molecules are moving. There's even an equation, not that you should remember this equation, it's not a part of this course, but I thought you might enjoy seeing the equation that's formal. The average velocity of the molecules in a gas is equal to the square root of 2 times this constant K, called Boltzmann's constant, times the temperature divided by the mass of the molecules, the mass of the individual molecules. 2 kT over m square root tells you the speed. So temperature, if you look at this equation, maps directly into velocity. You tell me the temperature and the mass of the molecules, I can tell you the average speed of those molecules. Now, why is it that we use the word temperature for speed? Well, it's because when you walk outside on a hot day, you walk out the front door, the molecules in the air are moving around randomly, and they bang into your skin. And your skin has neurons, and it senses the collision energy. And so your skin is actually sensing when you feel hot. Your skin is actually sensing the typical speed with which the molecule is hitting your skin, and the neurons in your skin are saying, whoa, I just got bumped by a really fast-moving molecule. Your brain senses that, and you say, wow, it's really hot today. What you really mean is, wow, the typical temperature of the molecules is very high today. That's what you really mean. Your brain is actually sensing the average speed of the molecules. That's temperature. Here's a little quiz. You might know the answer to it. Cool gas, hot gas, slow-moving molecules, fast-moving molecules. In a refrigerator, food is preserved. Why? Want to show me your answers? I think most of you have the right idea. The right answer is A. The reason we cool down food in a refrigerator is so that the molecules move more slowly, and so any chemical reactions that might involve the bacteria that would be reacting and growing, they go more slowly. The chemical reactions that cause the food to degrade goes more slowly because the molecules are colliding and reacting more slowly. So we cool down food to keep the chemical reaction rates and biochemical reaction rates as low as possible so that the food stays preserved. It doesn't degrade. So that's a direct result of the speeds of the molecules. Now, what about pressure? What actually is pressure? We talked about temperature. What about pressure? This is a little trickier. We all know that when you blow up a balloon, there's pressure in the balloon. If you want to put air in the tire of your automobile, you want to bring the air up to a certain pressure, like 32 pounds per square inch. That would be a pressure in an automobile tire. But what is pressure, really? Well, pressure formally is the force per meter squared per area caused by the molecules in the gas or the atoms in the gas. What does that mean, force per meter squared? What in the world does that actually mean? Well, here's the idea. The molecules, like the air molecules in this room, are moving around with random directions and a range of speeds. If you look at this blackboard here, and you look at a square of this blackboard, let's say 1 meter by 1 meter, hitting this square are, of course, molecules of air. They're banging into the blackboard, colliding, bouncing off, colliding, bouncing off. There are 10 to the 20 such collisions every second by all the molecules hitting this board. And you might think to yourself, when a molecule minding its own business collides with this blackboard and bounces off, the molecule was going that way. Now the molecule is bounced off and is going back the other way. And you know from Newton's laws, for every action, there's an equal and opposite reaction. So the momentum, literally, that the molecule had when it hit the blackboard got reversed. Where did that momentum go? It went to the blackboard. If the blackboard were a little thin sheet of saran wrap, every time a molecule hit that square meter, the saran wrap would recoil backwards and recoil backwards, ping, 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 ping. Every time a molecule hits that blackboard, the blackboard is recoiling backwards because the molecules are delivering their momentum to the blackboard. And this is happening 10 to the 20 times per second. So even though molecules individually don't carry very much momentum because they have so little mass, cumulatively, as an aggregate, they're pushing on that square meter with a legitimate force. It's a force because momentum is being transferred from the molecules to that patch of blackboard. And it's that force per square meter that we call pressure. It comes from individual molecules, one after the other, hitting a surface and delivering momentum. So pressure is nothing more than the cumulative momentum of each of the molecules colliding with a surface and pushing with a force per unit area on that surface. Here in the United States, we use lunatic units of force per unit area. The force is in units of pounds, icky. The area is in units of inches squared, that's icky. But that's what we do in the United States, pounds per square inch. In the whole rest of the world, the units of force are newtons, and the unit of area, of course, is the square meter or square centimeter. Either way, it doesn't matter. It's force per unit area. Here at the surface of the Earth, every square inch is feeling a force of 14.7 pounds. Every little square inch on your body, a little square inch, is feeling 14.7 pounds of force. It's as if somebody were standing on your arm at every square inch, weighing 14.7 pounds. That's how much atmospheric pressure there is. And of course, it's that pressure that answers the question about what holds up the Earth's atmosphere. The Earth's atmosphere, you might think by pressure it would, just float away. Or you might also worry that the Earth's atmosphere, being composed of molecules, each of which has mass, that maybe the Earth's atmosphere would just fall down by gravity. And of course, the reason the Earth's atmosphere doesn't fall down by gravity is that the gravity that acts on the air molecules is balanced by pressure. And there's a perfect balance between pressure and gravity in any atmosphere. By the way, also in the ocean. Any fluid that's sitting there stably, there's a balance between the pressure that's pushing outward and would cause it to just expand, and gravity that holds all of the molecules individually into the planet. Perfect balance, it's called hydrostatic equilibrium, and it allows you to really appreciate the pressure structure of an atmosphere or an ocean. Here's a little quiz question. It's an easy one. It's sort of silly. Suppose the Earth's atmosphere contained twice the number of molecules that it does. Compared to our Earth, the pressure on the surface would be, answer, it's an easy, obvious one. If there's twice as many molecules, there are twice as many collisions. If there were twice as many molecules in the Earth's atmosphere, there would be twice as many collisions hitting the board, and it would experience twice the momentum transfer, and hence twice the force, and hence twice the pressure. So more molecules means more pressure, proportionally. I've mentioned layers in the Earth's atmosphere a few times. I want to zoom in because there's something amazing about the Earth's atmosphere that bears on international politics. And here it is. Here's the Earth's atmosphere. There's where you live, the troposphere. The next layer up is the stratosphere, then the mesosphere, thermosphere, and exosphere. They are each important, and I want to go through them one after the other. First of all, pressure and density decrease with increasing altitude. I think all of you know this, but let me say it again. As you go hiking up into the mountains, you know that the higher you get, the lower the pressure, the lower the density of the air. Air gets thinner and thinner as you get up. That's a result of hydrostatic equilibrium. What do I mean by that? Well, when you're up high in the Earth's atmosphere, the gravitational force pushing down from the molecules above you is less, because there's less Earth's atmosphere above you. So when you're high up on a mountain, there's less atmosphere above you, so there's less gravitational force pushing down that upper atmosphere, and therefore there's less pressure pushing up. Less gravity means there must be less pressure, so that they're in balance. So pressure and density decrease as you move upward. Temperature, however, does not monotonically get hotter or cooler. Pressure does both, and I'll mention that in a moment. Here, if you look at this graph, and I'm going to tell you something right away, I think this is about the most complicated graph I'm going to show all semester. Let me tell you what it is, and it's not that bad, but it's a little wacko. Here's altitude in kilometers. Here's the ground, 10 kilometers, 20, 30, 40, 50, 60, up to 120, up to 350 kilometers above the Earth's surface. And on this axis is the temperature at each of those layers. Temperature in degrees Celsius, 0, 20, 40, minus 20, minus 40, minus 60. Here's how you interpret this graph. As you move up in the troposphere right here, as you move up, you read over and you can see what the temperature is. At the ground level, the temperature is maybe 10 or 15 degrees Celsius, depending on what kind of a day it is. As you move upward, the temperature drops. You see, this line going here means lower temperature. So in the troposphere, it gets colder and colder the higher you get, and all of you know this. You've gone hiking in the mountains, and you know that when you go hiking to higher and higher altitudes, it gets colder and colder. There's a reason for this, but I'll get back to that later. So in the troposphere, temperature drops with increasing altitude. But in the stratosphere, look what happens. As you go higher, the temperature gets hotter and then colder. Hotter and then colder. And there's an important reason for this. In the stratosphere, the air molecules are heated by ultraviolet photons coming from the sun. And in fact, they are absorbed very efficiently by the stratosphere. I just said something that contradicts what I said earlier. I said the Earth's atmosphere is nearly transparent. What I didn't say is that, yes, it's transparent in visible light. In ultraviolet light, it turns out the ultraviolet light coming from the sun is absorbed very efficiently in the stratosphere thanks to one particular molecule called ozone. Ozone is a molecule that has not 2 but 3 oxygen atoms. And I'm going to come back to that in a second. Before I do, I'll tell you what's in the mesosphere and the thermosphere. There, it's the X-rays from the sun that get absorbed very efficiently heating the Earth's atmosphere. And where's the edge of the Earth's atmosphere? Where's the outermost edge of the Earth's atmosphere? I don't know. It's nowhere. The Earth's atmosphere just peters out, getting less dense, less dense, less dense, asymptotically approaching zero density. But the Earth's atmosphere never has an edge to it at all. Now, may I go back to the stratosphere and this amazing ozone that exists there. Ozone molecules, oxygen that has 3 oxygen atoms in it, very efficiently absorbs UV. Thanks to the ozone that lives in the stratosphere, the UV light that would cause mutations in you every day gets absorbed. Unfortunately, there are human-made synthetic molecules that break apart the ozone, wiping out the ozone. And here's a little video that shows this. There's O2, there's chlorine, there's some oxygen. Hang on. And here is an ozone molecule, 3 oxygen atoms, with some UV radiation coming in. And what happens is these man-made molecules give chlorine to the ozone, stripping off one of the oxygen atoms, so that what was 3 oxygen atoms, aka ozone, now has only 2 oxygen atoms. And the ozone is destroyed, and it no longer absorbs the UV light. So human-made CFCs, as they're called, chlorofluorocarbons, deliver chlorine to the atmosphere, and the chlorine atoms strip off an oxygen atom, destroying the ozone. And now with less ozone, the UV light can make it through the Earth's atmosphere. Any of you that's ever been to Australia know about this, because if you go to the beach in Australia, there are signs up that say, beware of UV light that can cause cancer in your skin as well as mutations. It's because in the southern hemisphere, the ozone destruction has been worse, and so people suffer more from the increasing ultraviolet light that hits near Australia more than anywhere else. And it's even worse in the Antarctic. You see here a graph of ozone over the course of time. During the 1960s, 70s, 80s, and 90s, the amount of ozone in the Earth's atmosphere was dropping off catastrophically. This is political because it was we humans that were causing our own health hazard by destroying the ozone. There were international meetings. Countries all got together in giant international meetings, and they constructed international laws to stop the production of these chlorofluorocarbons, the so-called CFCs, these critters here. And countries began banning the CFCs because they were destroying the Earth's ozone. It was a wonderful example of international cooperation. The CFCs have been greatly curtailed, decreased in their production, and as a result, ozone is coming back. So the Earth's atmosphere is being revitalized, re-enriched with ozone. It's a great example of how we humans can get together, solve problems internationally that otherwise would pose a global health problem. Now, of course, we also owe a lot of our existence to energy balance. The Earth's atmosphere is lukewarm, and that's because energy is balanced in the Earth's atmosphere. Our planet and other planets absorb the light energy from the sun that we've talked about. That warms the surface of our planet Earth to some equilibrium temperature. As the Earth's surface warms up, thermal emission allows the Earth to emit more infrared light. Earth warms up, it emits thermal emission, more infrared light, and of course that greater emission of infrared light cools the surface. So balancing the heating is cooling, and the cooling is from the planet's surface emitting light energy in the infrared by thermal emission. And therefore the surface cools back down. And eventually an equilibrium is achieved. And I'm going to mention this in words rather than show a graph. Think for a moment about the great thermostat that we enjoy here on the Earth. If too much sunlight comes in, you might worry that the Earth would heat up. But if too much sunlight comes in, the Earth gets hotter, there's more thermal emission in the infrared, and the Earth radiates away that extra energy that came in, thereby cooling the Earth back down. More energy in means a higher temperature, and therefore more thermal emission to cool the Earth. Same the other way around. If the Earth somehow or other got less sunlight, maybe because there's clouds, maybe because of a volcanic eruption that blocks the sunlight, if less sunlight hits the surface of the Earth cools down, there's less thermal emission, and so the Earth loses energy less efficiently. And again, you achieve balance. Less energy in, but now as a result, less energy out. And so the Earth has a way of achieving its own thermostatic equilibrium, just like a thermostat in your living room. It's a marvelous regulatory effect to keep the Earth in thermal balance. I had mentioned earlier that pressure and gravity were balanced, but here I'm talking about the thermal energy, the heat of the Earth's atmosphere that also is regulated and always kept in balance. The absorption of energy is balanced by the thermal energy to give the Earth a stable temperature. And again, if the Earth got too hot, it would be able to correct itself. I'm going to stop today's lecture right here. This is a perfect place to stop. Thursday's lecture is going to be one of the most important of the semester. We're going to talk about the greenhouse effect, global warming, and global climate change.